Magnetism basics and magnetic forces on moving charges. On the two figures, draw needles on the compasses to show the direction of the magnetic field at each location around the two magnets shown. A compass needle is a tiny magnet, and it is going to be directed tangent to any magnetic field line. If this compass is perfectly axially lined up with this bar magnet, the north pole of the compass will point directly like that. Magnetic field lines run away from the North Pole and toward the South Pole on the outside of a magnet. So this compass might be directed like so. This compass is going to point like so. This compass will point just like that. This compass will point maybe something like that. And this compass points something like that. These compass needles will be tangent to the field lines. What about here? Well, here, this compass needle is going to point away from the North Pole. This compass needle will point toward the South Pole. Magnetic field lines would go what kind of maybe in that tangential direction right there, and maybe in that tangential direction right there. On the figure for part B, and I've reproduced that right here, draw a circle about this big. Okay, right about there. On the imaginary line that would connect the letter N with the letter S, this circle represents a current-carrying wire that runs into and out of the page between the poles of the horseshoe magnet. We want that wire to experience a magnetic force that pushes the wire to the left. The force on this current-carrying wire, we want to act to the left. Within the O, draw a symbol to show the direction conventional current would have to travel. The magnetic field lines, as we know, outside of a magnet run from the North Pole to the South Pole. So there's your B field right there. And we want the force on this thing to be directed to the left. So the question is, in what direction is there current going in this wire? Is it coming towards us or is it going away? And so we want to use our pat-pat right-hand rule, which says that our right thumb is going to go in the direction that the current is traveling, and our fingers are going to point in the direction of the magnetic field, and then we're going to pat in the direction of the force. So that means if I'm going to pat to the left and my fingers are going to be directed towards the top of the screen, you see thumbkin is coming out at us. Put a little dot there. There you go. That means that that current is going to be coming towards us. Should I label it with an I? Label the north and south poles of the magnet such that the magnetic force on the wire would be toward the top of the page. Very similar type of question. The magnetic force is toward the top of the page. In what direction must the magnetic field act? In other words, which is the north pole and which is the south? I'm going to use our right-hand rule again. The force is toward the top of the page, and the current is going into the page. My thumb is going into the page, and I'm forcing pat to the top. So you see my fingers are pointing to the left, and magnetic fields outside of a magnet point from north towards south. So I think the north pole is on the right there. In which direction will this wire be pushed? Well, let's see. Right about here, there will be a magnetic field line. Of course, these are up and above and below, they're going to curve. But right here, right at that wire, the magnetic field is directed to the left. So in what direction will this be pushed? Let's use our pat right-hand rule one more time here at least. We're going to have our thumb coming out of the page at us. Thumb coming out of the page. Magnetic field lines are the fingers, and they're pointing to the left. So the pat is going to be down. Magnetic force is going to be acting down. Which direction will this wire be pushed? Same idea. Thumbkin is going in the direction that the charge is moving. Our fingers are going to point towards us. You check it out. I can't show it on the camera, but there's going to be a magnetic force to the right here. Last little sequence. We're going to change it up a bit. Here we have an electron, and it's about to enter a region having a uniform magnetic field. In which direction will the magnetic force act at the first moment the electron enters? This velocity vector has two components. It has a horizontal component, you might say, and then it has a vertical component. That vertical component, nobody cares about because there's no magnetic force due to that component. It's only this one here. And since we have a negative charge, we have to use our left hand this time. I'm going to point my left thumb to the right. I'm going to point my fingers to the bottom of the page, and then I pat towards the camera. In which direction will the magnetic force act? It's going to act towards the camera. And lastly, describe in some detail the trajectory of the electron once it enters the field and then afterwards. The vertical component, we said, is completely not changed. Points towards the top of the page the whole time. But the direction of the horizontal component, now, not the magnitude of this horizontal component that I'm pointing at. Its magnitude won't change, but its direction will. And that direction will be constantly changing. In a sense, we're going to get a corkscrew path that this electron will follow, assuming that this magnetic field goes on for a while.